Oo nga, revolutionary siya dahil sa discovery niya ng gravity.
Uy, alam niyo ba, minention niya ni Thomas Kuhn sa book niya, yung title, The Structure of Scientific Revolutions.
Hi, we are Jas.
And Jet?
And today, we'll be talking about Thomas Kuhn's work, The Structure of Scientific Revolutions.
Let's start!
So today, we'll explore the fascinating world of scientific revolutions through the lens of Thomas Kuhn's groundbreaking work, The Structure of Scientific Revolutions. In this presentation, we have outlined 3 key objectives to guide our discussion. Firstly, we aim to define normal and revolutionary science and also determine their differences. Secondly, we will delve into the concepts of paradigms, exploring what they entail and how paradigm shifts come about. Lastly, we will explore a few examples of scientific revolutions to deepen our grasp of the concept. Through these objectives, we will gain a comprehensive understanding of the dynamics that shape the evolution of scientific thought. Before talking about the book itself, let's get to know first the man who wrote it. The author of the book, Thomas Samuel Kuhn, was born on July 18, 1922 in Cincinnati, Ohio, and died on June 17, 1996 in Cambridge, Massachusetts. Actually, he was initially a physicist with a Bachelor of Science degree, a Master of Science, and a Doctor of Philosophy in Physics, all from Harvard University in 1943, 1946, and 1949 respectively. However, he became more well known as a historian and a philosopher of science because of his famous work, The Structure of Scientific Revolutions. Moreover, he taught history and philosophy courses in institutions such as Harvard University, the University of California, Berkeley, and Princeton University throughout his career. All in all, his academic background in physics, alongside his interest and opportunity to work in the field of history and philosophy of science, allowed him to make significant contributions to our understanding of how science evolves and the roles of paradigms in scientific revolutions. Moving forward to the book itself, The Structure of Scientific Revolutions was a book about the history and philosophy of science published in 1962. It contained historical case studies such as the Copernican revolution in astronomy and the shift from classical to modern physics to illustrate Kuhn's ideas. The work was also considered both controversial in its time and influential in its field from then on. Causing a considerable amount of controversy and sparking lengthy discussions among supporters and critics, the book underwent at least 3 major revisions and was translated into 16 languages in order to reach a global audience. But mainly, the work had a significant and lasting impact on the philosophy of science, affecting how scientists and academics perceive the development of scientific knowledge, and it has remained an essential work in several academic disciplines. To grasp the central concept of the book, it's essential to explore its origins first. Let's begin by examining the traditional view of scientific development and how Kuhn responded to or critiqued it. Traditionally, scientists thought that science develops in a linear progression as a process of accretion, with incremental progress contributing to the growing body of knowledge in science. However, Kuhn had 2 points. First, he identifies a problem in the history of science concerning the attribution of discoveries and the individuals responsible for them. And second, he acknowledges that the traditional view of scientific progress as a cumulative process is still true, but he introduces the idea that scientific development also includes revolutionary changes and paradigm shifts, challenging the linear accumulation of knowledge. Now, let's dig into the central theme, Thomas Kuhn's perspective on scientific development. Kuhn explains that scientific development is a non-linear process that includes 2 alternating phases: normal science and revolutionary science. First, we have normal science. Normal science refers to the idea of linear scientific development where the scientific community works on an existing paradigm. Second, we have revolutionary science. In contrast, revolutionary science represents the non-linear aspect of scientific development where a new paradigm emerges that challenges the scientific community's existing paradigm. Now, revolutionary science and scientific revolution may sound similar, but they are distinct concepts. When we refer to revolutionary science as a phase, scientific revolutions, on the other hand, refer to the periods in the history of science where new paradigms have been accepted by the scientific community and have replaced old paradigms. Again, scientific development, according to Kuhn, is divided into two alternating phases. First is normal science, and then revolutionary science, where scientific revolution happens. Normal science cites what happens in a linear and traditional viewpoint of scientific progress, while revolutionary science defines Kuhn's idea wherein significant and groundbreaking changes occur in established scientific theories, beliefs, or paradigms. Up to this point, I've used the term paradigms several times already. But what precisely do we mean by paradigms? Truthfully, the book doesn't provide a single formal definition for the term. However, Kuhn described paradigms in various ways throughout the book, and I have here a mind map to help you visualize it. So first, paradigms represent significant achievements in the history of science and are the best available explanations during a particular phase of scientific development. Second, metaphorically speaking, paradigms are like boxes or cages that confine the scientific community's research within a defined framework, shaping their approach, questions, and methodologies. And third, existing paradigms in normal science are supported by the foundational principles and laws outlined in textbooks. They are models serving as guiding references for the scientific community's further research. And as new discoveries accumulate, this body of knowledge reinforces the existing paradigm. Well, that concludes my portion, and to further elaborate on this discussion, let's have Jet.
Hi everyone, this is Chet. Now we're gonna talk about the fourth chapter of this book, The Structure of Scientific Revolutions by Thomas Kuhn. And the fourth chapter is titled Normal Science as Puzzle Solving. So, let's start with this statement and the following questions. Kuhn associates normal science with puzzle solving. What's so similar with puzzle solving and normal science? So the first question is that, why is normal science similar with puzzle solving? And the second question is, what are the rules of a paradigm? Okay, let's continue. So let's start by answering the question, what is similar with normal science and puzzle solving? So here, we have Kuhn's jigsaw puzzle metaphor. Let's read. When someone begins solving a puzzle, they always try to arrive at the already determined solution. What does that mean? For Kuhn, the solution or the answer is the image itself. It's the picture itself that you're trying to build if you're solving a jigsaw puzzle. There are many ways to solve a jigsaw puzzle. It depends on who might solve this puzzle and where would they start. Some solve puzzles faster than others. Everyone has a different strategy. So this means that in normal science, there are people or there are scientists that approach a problem or approach a scientific problem in many directions and many approaches. So the similarity here of jigsaw puzzles and normal science is that others might finish the puzzle faster than other people. In normal science, some scientists might answer the problem faster than other scientists, but they arrive in the anticipated in a new way. That's what Kuhn said. There's already an answer. You just have to, go through the process of experimenting, approaching, and brainstorming, and researching. But there's already an answer. There's already the anticipated answer. So here, Next slide, we have a segue question. Why are scientists so passionate about normal science? Why? Why do they want to pursue this? If the answer is already there, why are we doing this? Why are scientists doing this? Notice the highlighted words on the thought bubble: altruism and fame. So for Kuhn believes that scientists are motivated by a desire so that people will admire their intelligence rather than novelty. So what this means is Kuhn believes that scientists are pursuing normal science as a way for them to gain admiration, fame, so that people will admire their work, their skills, their intelligence, rather than their novelty and altruism, or their being selfless. So in Filipino, ambag sa bayan. Okay? So that's what Kuhn said about this, about pursuance of normal science. So the next question that I told you a while ago was, what are the rules of a paradigm? Or what is the rule of a paradigm? So here we have two categories of rules. Let's read them. Paradigms usually dictate the methods and technologies that should be used to obtain information. So here, it's true that paradigms should be able to dictate the methods and technologies used, because paradigms cause revolutions, scientific revolutions, right? So they should be able to dictate what type of experiment, what type of technology, what type of machine a scientist or a researcher might use to obtain that answer, to obtain information. The next rule is that there are higher level quasi-metaphysical beliefs that help each paradigm. So what does the term higher level quasi-metaphysical means, right? Okay, let's give you an example so that we'll understand what this means further. So for example, Cartesian thinking by René Descartes. We all know that René Descartes gave scientists both a metaphysical understanding of the universe and the cosmos, but it also gave a concrete way of problem solving. The metaphysical term there was that René Descartes helped people to understand what the universe is made up of and what it isn't. But the concrete way of problem solving is when you apply his philosophy to your everyday, day-to-day life, when you solve simple problems. So that's what higher level quasi-metaphysical beliefs mean. Okay, now let's move on to the fifth chapter, titled Priority of Paradigms. So it is said here that it is easier to isolate a paradigm than it is to articulate that paradigm's rules. In other words, scientists may agree on a core set of principles but disagree on how those principles should be put into practice. As normal science becomes more precise and focused, Kuhn finds it simpler to trace these broad paradigm founding ideas through history, because he was an historian as well, than to trace the more precise rules of a particular paradigm. Kuhn is also careful to note that there are numerous subfields and smaller paradigms within each larger discipline, and that modern science is not one cohesive study. As a result, there may be smaller scientific revolutions where one group reconsiders its paradigm and other larger groups carry on with their normal scientific practice. Kuhn tells a story about a well-known physicist and a well-known chemist. They were questioned on whether or not a helium atom alone was a molecule. Because each was relying on the distinct demands and expectations of their respective paradigms, the physicist responded negatively and the chemist positively. To give deeper understanding about a paradigm, let us discuss Ludwig Wittgenstein's idea of family resemblance and its similarity to understanding paradigms. So, paradigms are broad and have similar categories and fields. They may have common values and shared goals. However, normal science makes room for many more kinds of work. For example, Ludwig Wittgenstein's idea of a mother and a daughter that have the same eyes, ears, nose, mouth, and whatsoever, but they have their own specifics. They are different from one another, and that's what paradigms are for Kuhn. It is similar with Ludwig's idea of family resemblance. Now that we're done talking about chapters 4 and 5, let's now go to Jasmin to understand what paradigm shifts are.
Next, we will be discussing the chapter 6 of the book, which is the anomaly and the emergence of scientific discoveries. When most people think of science, they usually envision normal science. Is it cumulative, linear, and highly efficient at gathering answers? But how does normal science, which avoids novelty, end up producing scientific revolution? In the book, Kuhn previously stated that scientific progress is cyclical, which means from normal science to crisis and then back again. He argues that this cycle occurs for a reason, because crisis cannot occur without the traditionalism or the fear of novelty inherent in normal science. It is only by following a specific set of rules may new ways of thinking arise. Paradigms with their rules and predictions teach scientists what to expect, so when something does not go according to their expectation, the normal scientists notice, and so anomalies are easier to spot the more established a paradigm is. A paradigm shift, according to Kuhn, is the process of discovering an anomaly and changing assumptions and rules to explain that anomaly. The paradigm shift is over when the anomaly becomes accepted rather than novel. Scientists are blurring the lines between the real and theoretical discoveries by focusing their attention on the anomaly. Kuhn uses the history of oxygen science to demonstrate this. Many different scientists were attempting to comprehend oxygen in the 1700s. Some were attempting to isolate one gas from the other gases in the air, while others, such as Lavoisier, were attempting to make sense of oxygen in terms of atoms and chemical energy. The discovery of oxygen by Lavoisier initiated a paradigm shift. When Lavoisier began to notice an anomaly, his discovery of oxygen gave shape and form to the new paradigm that would allow him to deviate from the received one. Many of Lavoisier's contemporaries, however, could never understand his work since they were all still convinced in the old paradigm. The invention of X-ray machines is another example of discovery through anomalies. Wilhelm Röntgen was testing cathode rays when he noticed light blazing in an unexpected region of his device. This surprise spurred him to create the X-ray, which eventually opened up to totally new avenues in science. But once again, other individuals had seen that unusual radiance before Röntgen, but they had dismissed it because it contradicted their established paradigm concepts. Many people were frightened and outraged by such a radical new concept. Worse, equipment that had previously been evaluated in one way now had to be viewed in another, resulting in past scientific work being dismissed and confused. Kuhn uses this example to argue that using a specific machine with a specific lens carries an assumption that only certain types of circumstances will arise. These assumptions are necessary for normal science to proceed, but disrupting these assumptions is what allows for entirely new ways of understanding the world. The Leyden jar, or a major experiment in the field of electricity, is the final example of an anomalous discovery given in the book. Though efforts to build this jar were led by the fluid theory of electricity, common in the 1700s, scientists discovered the much more beneficial idea of electrical conduction during the entire building process. Additionally, Kuhn then uses a psychological experiment to argue that the longer someone pays attention to an anomaly, the more forced they are to recognize and further explain it. People in the experiment were shown some standard cards as well as some unusual ones, such as Black four of hearts. So participants first thought the anomalous cards were normal, but by the end of the experiment, they had rethought that the entire structure of a deck of cards. Finally, Kuhn argues that developed and specific paradigms facilitate this type of resistance. Only when scientists are seeking for very little exact things will they detect that those things are behaving strangely. As a result, the more rigorous a scientific paradigm, the easier it is for scientists to detect an anomaly. This is why scientific revolutions always emerge from normal science. The last chapter that we are going to discuss is the chapter 10, Revolutions as Changes of Worldview. Paradigms guide scientists on where to seek and how to interpret what they notice. An example of this from the book is turning a bird's sketch sideways exposes a completely different picture, an antelope. Thinking in terms of a new paradigm brings in a new world. Therefore, Kuhn underlies another aspect of scientists' humanity here. How they move through and experience daily life is influenced by their professional work. Kuhn's point out using the science of Gestalt psychology, or a whole that cannot be broken down into component parts, that once people have viewed the world in a new light, it is nearly impossible for them to return to their previous perception of it. Kuhn also uses Uranus as an example of a celestial entity that has sparked great controversy among the astronomers. Since they did not notice Uranus' motion, several different observers regarded it as a star throughout the 1700s. When one scientist observed it move, he thought it was a comet. Scientists recognized Uranus as a planet after months of unsuccessful attempts to incorporate it into existing comet theories. Suddenly, after accepting Uranus as a minor planet, astronomers began to notice other minor planets and asteroids all over the place. Therefore, Kuhn claims that when scientists changed their minds on Uranus, they looked up at the sky and discovered different things. Accordingly, Galileo was the most remarkable example of this shift in perception. Aristotle described the pendulum by stating that heavy items fall naturally and the object at the bottom of the pendulum is simply falling slowly due to the chain holding it back. Galileo, on the other hand, began to regard the pendulum as a swinging body that repeatedly performs the same action. The new viewpoint on the pendulum enabled Galileo to develop several important scientific theories concerning weight, incline, and velocity. Therefore, Kuhn states that neither scientists nor laymen learn to see the world piecemeal or item by item. For example, a kid learning to call her mother mama is also learning about gender and family structures in general. Because paradigms do not determine single facts or experiences. Paradigm shifts affect multiple concepts and perceptions all at once. Furthermore, science in the new paradigm uses many of the same techniques, tools, and terms as science in the old paradigm. However, when the same procedures and technologies are used in a new paradigm, they are known to reveal significantly different information. To demonstrate this, Kuhn examines John Dalton's scientific revolution. For much of the 18th century, chemists relied on affinity theory, which held that certain chemicals dissolve in others due to an underlying attraction. Some chemists realized around the end of the century that a few chemical mixtures had set proportions of their ingredients. However, no unified theory was developed, and the discipline began to fragment, appearing more like pre-paradigm science. Therefore, Dalton was ultimately responsible for the demise of affinity theory with his famous atomic theory. Dalton was able to create the law of fixed proportions since he came from a different discipline, that all atoms will connect to one another in simple or whole number ratios. Simultaneously, Dalton's theory permitted him to assert that if the elements in a compound were not in this ratio, the substance was not chemical. Though some chemists were deeply opposed to Dalton's view, this new paradigm quickly proved more useful and efficient. Since even skilled scientists had been conducting their experiments with different goals and ideas under a different paradigm, Dalton had very little evidence for his theory initially. Instead, the evidence came after by the future scientists.
In essence, Kuhn's work urges us to recognize that the progress of science is not a smooth, continuous path, but rather a series of revolutionary leaps that fundamentally alter our understanding of the universe. The structure of scientific revolutions continues to be a cornerstone in the philosophy of science, reminding us that science is a dynamic, evolving enterprise shaped by the paradigms that define its boundaries and the anomalies that push those boundaries forward.
Wow! Ang dami nating natutunan tungkol sa normal science.
Tungkol sa paradigms.
At paradigm shifts.
That's it. See you next time.